In this installment, we want to examine the effect that elliptical orbits has on an important quantity, and that's energy. The energy involved in the Earth-Sun system. So what we have here is clearly a very exaggerated ellipse, based on the last installment we had. We have our sun, like so. We have the Earth at a location called the perihelion. And the perihelion, this peri, means close. The perihelion is where it's at its closest to the sun. As it travels in its orbit around the sun, the Earth gets to this location, the greatest distance, and that is called the aphelion, not aphelion. You'll see people pronounce it aphelion, but that's incorrect. It's aphelion, and that means it is the farthest. So if we now imagine a concept like gravitational potential energy, if we were to take the Earth in this location and bring it closer, it would have less gravitational potential energy than when it's farther away. So as we move the Earth farther away, we get greater gravitational potential energy. Just like a person on the Earth, if we move them farther away, we'll have greater potential energy. And we see that here in the case of the moon's orbit, where there is a perigee, closest part of the moon to the sun, and apogee, where the moon is farthest from the Earth. And so if we had an astronaut who was traveling from the Earth to the moon, as they recede from the Earth, their gravitational potential energy will increase until they get at their greatest location. And as they come closer, their gravitational potential energy would decrease. But we know the law of conservation of energy says the total energy of the system remains constant. So if we are increasing the gravitational potential energy in this direction, that means that energy has to come from somewhere. Either there is some work being done, or it's being transformed from one form of energy to another. And this is where we invoke, as we very often do when things are changing heights. In this case, is we have gravitational potential energy here, gravitational potential energy dominated, and kinetic energy here, such that the total energy is equal to the kinetic energy plus the gravitational potential energy. And that total remains constant. And in this particular case, they do not become zero at any point, neither becomes zero. So we have an object, as it comes from here, which has dominated by kinetic energy. That kinetic energy gets converted into gravitational potential energy. So now there's less kinetic and more gravitational. And then that gravitational energy gets converted to kinetic. So we have this oscillation back and forth between gravitational potential and kinetic energy. But that also means that it's slower at a great distance, and it is faster at a closer distance. So that's the moon and the Earth. And we look at the Earth-Sun system, the same thing happens. So over here we have, it is fast. It's kinetic energy dominated, the Earth. And out here it's gravitational potential energy dominated. So if the orbital direction is this way, we have kinetic energy decreasing as the gravitational potential increases. And then it's traveling slowly. It is slow out here, and it is fast down here. And that gravitational potential energy gets converted to kinetic energy, back and forth. Now, of course, this is exaggerated because the ellipse is so extreme. It's exaggerated, so the ellipse is so extreme. But we can graph this. We can graph this. So on the bottom, I've created this chart, which is, we could label it time or theta. And we can have our energy on the vertical axis. So let's say at time 0, we are in this location. The Earth is over here at time 0. And what we know is that the kinetic energy is at a maximum. So we'll draw kinetic energy in red. So kinetic energy is at a maximum at theta 0. Now when we get to halfway through the cycle, we know it's at a minimum. That's halfway through the cycle. And by the time we return to the end of the cycle, kinetic energy is a maximum. If we are to smooth this curve out, what we would see is it would behave like so. Should probably redraw that because that's not so good. And what we can see then is the kinetic energy is a function of cosine. It is scaled by cosine. Let me write that a little bit differently. So there is a maximum kinetic energy, the kinetic energy maximum, times the cosine. So when the theta of the cycle is 0, it'll be at a maximum kinetic energy. And when we get to pi, it will be a minimum. Now let's plot the gravitational potential energy. The gravitational potential energy is a minimum at time 0. And it is a maximum when it is halfway through the cycle, and then it returns to being a minimum at the far end. So if we were to smooth this out, look like this. And that function looks like sine. And let me redraw that. Now we'll leave it like so. And so gravitational energy, the gravitational potential energy max, is a function of sine, and it's scaled by sine. When we look at the total energy, well, total energy is sum of the kinetic energy plus the gravitational potential energy. And what we could see here at the beginning is then green plus blue, red is blue. But we noticed that a little bit time later, green plus red equals this. And over here we're equal to this. And over here we're equal to this and this. And so what we see then is that the total energy remains constant. All the while, it's changing back and forth between kinetic and potential. But the total energy of the system remains constant. And this is an important concept that we'll see again and again throughout the rest of the course. And one thing I just forgot to mention in the beginning is that the first letter of a word A, when it's A like aphelion or apogee, it's a word-forming element that means away, from the Latin a, which means off or away from. So whenever a word begins with A like this, it usually means away. So apogee is far away and aphelion is far away. And so that is energy in elliptical orbits.